All right. How you guys feeling? How'd the homework go? Is it okay? We'll see. All right. And of course, I made the exam a few days ago to be ahead of schedule, so you'll have that next week. My TA has it right now. I already forgot what all I put on it. So I was just thinking to myself, I wonder what kind of membrane question did I put? So I'll have to go back and check on that. But you're welcome to ask me today. Unfortunately, I can't take any suggestions on what to put on the exam because it's already made. And unfortunately, I can't remember everything on the exam because I forgot a little bit. But it's probably good news for you that have recently thought about it. So I might let a few things slip or who knows what. So anyway, feel free to ask me any questions. As usual, my default is going to be to go through the recent homework solutions with you, to have something to cover, to answer any questions that come up. And I think at least a fair bit of it will be quite relevant. I mean, all of it will be relevant, but to the problems you'll have on the exam. You're also welcome to ask me if you wanted me to go back and touch on some things that we had to go a little quicker over. Let me know. Mentioned last time, but the scoring will be 70% of it will be kind of quantitative, show your work type of questions. 70% of the points available, 30% of the points will be multiple choice. None of those multiple choice or true false have calculations, like big calculations involved. So I made that change from last time. And I think there are 9 true false / multiple choice questions for you to answer. About 3 for each kind of subtopic that we covered. And then I believe there are 3 questions that require you to provide solutions and quantitative answer. All right, so with that, any other big questions? It's covering granular filtration, membrane filtration, and disinfection. All right, so we'll hop into the solutions then. All right, so the first problem is set up so that we can compare how well a plug flow reactor does compared to a CSTR for disinfection. Kind of get our brains thinking about which one would we actually use if we didn't already CSTR. And we are tasked with designing a system, and ultimately we want a 3-log reduction, but be careful with this part because that's the end goal. And then we're going to take a look at a couple cases to see how close we get to that end goal. And then in the last problem, part C, we'll take a look at, okay, given our analysis, what would it actually take to get there? Okay, so we're going to take a look at how close a 100 cubic meter CSTR and a 100 cubic meter plug flow reactor would come to that design goal, that end goal, but the problem may accidentally mislead you to think that is already true. So we're designing it, meaning we are considering how big we need to make it to achieve that. Okay, so that's just kind of a side note about the wording here. And we're reducing cryptosporidium using ozone, and we are given a coefficient of specific lethality. We talked about that from in our last lecture. That would be the K when we have the K star being that particular K times the concentration of our disinfectant. Right, so this is the pieces that we put into our disinfection rate equation. That would kind of look like that, right? And when we are solving this for, let's say, a batch case, we have that in some volume. Okay, so that's our coefficient of specific lethality. That's K. We're going to assume the coefficient of dilution is 1. That would be the C to the N power. That is 1. Okay, good. The flow rate is 0.1 cubic meter per second. And we are given an ozone concentration of 0.42 milligrams per liter. All right, so then we need to answer the following questions. A is how much crypto will a CSTR with 100 cubic meter volume remove? And here's where we should clue in to say, well, if we thought the 3 log reduction was telling us that's already how much we're reducing, the answer would just be a 100-fold removal, or excuse me, a 1,000-fold removal, 3 logs, 3 log removal, done. But just keep that as a pause on the 3 log. That's a design, something we are aiming to design. So we could say we want 3 log, but let's check. So for this particular scenario, we need to find what does that equal. Okay, does that make sense? Problem's not worded the best, but that's how it's set up, okay? All right, so then that's what we want. We want a mass balance that'll give us some form of N over N naught. And this is actually the amount remaining, right? So if this is what we have remaining, to get removal, we kind of need to do 1 minus the amount remaining. And to put it into percentage, if we want to, we could take that and multiply it by 100%. That'll get us the percent removal. Okay, so a 3 log removal would be 99.9%. So we want 99.9% removal, but really we don't know, and we're going to solve for how much this particular case gives us. Okay, so that means we need a mass balance. We've got a CSTR, and so for a CSTR, done this before, got a mixed system, we've got a flow rate coming in and going out. That means we have some number concentration coming in and not, and some N leaving. N would also be in here. We have some volume, and of course we can calculate our hydraulic retention time, theta, as V over Q. So theta then, volume is 100 divided by 0.1 cubic meters per second. This is 100 cubic meter volume. That means our theta is going to be 1,000 seconds. And by the way, if we use the same volume for our next reactor, that and the same flow rate, that will hold true. So theta will just be V over Q, no matter what shape we put it in. Okay, so there's our theta, in case we need it. But let's get back to our basics. We're going to assume it's steady state. So we'll have 0 equals what's coming in, Q N naught, minus what's going out, Q N, plus this reaction term, which is a decay because we're killing the stuff. So that'll be a minus in that volume with our constant, but we need to take our whole rate equation, right? We need to take essentially this term and put it here. So VKC for the ozone times that. Again, we could sub that as a K star if we want to, and then it'll feel very normal. I'll just leave it like this for now and do our typical derivation to get to an N over N naught, and then take 1 minus that. So we'll divide everything by Q. That's a pretty handy thing to do. N naught minus N minus theta K C N. Okay, if we do a little bit of derivation, you'll recall this ends up looking like N over N naught equals 1 over 1 plus, normally it's theta Kn. We also have that C here. Excuse me, theta Kc. Normally it's theta K. Okay, so there's the solution. What I skipped here was just getting the n's by themselves, factoring out the n, and dividing both sides by N naught, and then dividing both sides by the 1 plus theta K, C. So I just skipped a tiny bit. We've done this 100 times already. All right, so that's our solution there. And now we just need to take 1 minus that. So I guess we'll go ahead and put in the numbers here. When we put in the theta, put in the K, put in the C. This should become 0.074 remaining, 743. That's our n over n naught. And so 1 minus n over n naught would be equal to 0.926 removed. That's our fraction removed. So we have 92.6%. So either way would be fine. I didn't really ask for a percentage or a fraction. I just said how much removed. And that either way you could say that. Right, is that yeah.
Would it be acceptable if we didn't solve for the ratio in terms of retention time and just kept it in terms of flow rate and volume?
Yeah. Yeah. You could definitely take this and never solve for theta and just leave it as V over Q because you have V and Q.
And what about if it wasn't in percentage and instead if it was in terms of log removal, is that also okay?
If you reported this as log removal, this would be what, like 1.3 or something? It's 1 point something log. As long as you're clear and I can kind of see that, hey, you just took this from a fraction and took the log, like did a log transform, I should give you full credit for you, or you could come back to me and argue like, hey, look, I did it right. I just gave it. So yes, I would take that. That wouldn't be a problem, but might be easier just to leave it as 0.926 or something. Now, a lot of times we'll use log removal because it's an easy way to say our threshold is 99.999999, whatever. It's just a lot easier to say 6 log. Okay, but there wouldn't be any problems to say we achieved at least a 2 log reduction. Okay, does this make sense? Okay, so we're going to do the same thing on part B, except with a plug flow reactor. And so the real difference is what is our equation for n over n naught to get our remaining. We are still kind of keeping it in mind that the 3 log is our target, but we're not necessarily on that target when we're just comparing these 2 different reactors to see how close we are to that target. And then we'll take 1 minus n over n naught is kind of our goal here. Now in this case, we kind of do need theta because we're doing a plug flow reactor. The mass balance on a plug flow reactor will look a lot like a batch reactor. We're going to set it up and say that for the little batch reactor that's flowing its way through this plug flow reactor, we are doing our batch type kinetics. V dc dt equals negative K C N in that volume. We'll get rid of the volumes. We'll take the integration. And this should be dn dt. So if you didn't catch that, that's important because it's n that's changing, c is a constant. In fact, since c is a constant, we're going to leave that over to the other side. So we're going to do this just like normal. We will end up with our typical equation. Again, we could put this as K star, and that'll look exactly like our normal equation, as we'll get ln of n over n naught equals negative K star t. And we could then say n over n naught is going to be equal to e to the negative K star t, or KCT, whichever you prefer. Now, in this case, the t has to become theta, right? The amount of time this batch reactor is flowing through there, we're going to say this is our theta, which is 1,000 seconds that we solved earlier. Okay, so in that case, we can get our solution. So in this case, n over n naught I skipped ahead. I was looking at my answer to part C, and I was like, this is wrong. What's going on? Okay. If we put these together, by the way, this should be 0.0126 per second. Okay, so then n over n naught in this scenario would be a pretty small number. We have 3.88 times 10 to the minus 6, that portion remaining. And here's where it definitely may make more sense to put in the log form. 1 minus that would be 0.999999. I think that's 5 nines. 22 remaining or removed. So essentially greater than a 5 log removal, just over, or 99.9992%. Okay, and now you get the feel for why that log transform might be a little more convenient. So either one would be fine, and what we notice is that's way more than we needed in terms of like the design criteria. So if we make a plug flow reactor this big, well, maybe we could have made it smaller. If that's all we needed to remove, we could perhaps make things a lot cheaper, or you take a higher flow rate, or whatever. Whereas if we take a look at part A, the cryptosporidium with a CSTR, it didn't even get 2 logs. It was just over 90%. So 90% would be 1 log, and we needed 99.9% to be safe. So the CSTR is definitely not the right choice. Even a 100 cubic meter reactor didn't do the job. But the plug flow reactor then is way more than needed. And so finally in part C, we ask, okay, well, what is the minimum plug flow reactor, minimum volume for a plug flow reactor required to achieve that 3 log removal, these conditions? Okay, so in this case, now we do say n over n naught is exactly 0.0101, right? That 3 log change, that would mean 1 minus n over n naught is 0.999, or 99.9% removal. So we can do the same thing, and really the change here is the retention time, meaning the volume changes, right? The flow rate's the same. The only thing that's going to change here is our hydraulic retention time. So we are simply going to say, we'll just go ahead and leave it in the natural log, 0.001. We can set that equal to, based on our derivation a moment ago, negative K star, or Kc, times theta, which is V over Q. So we just need to solve this equation for V, and we'll get our answer. And when we do that, we should get a volume of 55.4 cubic meters. Yeah.
So I solved it by using a new retention time.
Okay.
And so I didn't solve it. Is that also okay?
When you say you put in a new retention time, you just took this and solved for a retention time and then solved for theta? Yeah, you did the same thing. It's just algebraically tiny bit different, right? So you could just say, okay, well, this is theta, so I'm going to solve for theta nu. Definitely doesn't have to be the same theta. And if I look at the volume here, it's just over half. So I'm guessing the theta nu is something like 550 seconds. Did you get something like that? Did you solve for it? Yeah, so somewhere around there. And then just say, well, the flow rate's still, so it's a new volume over your flow rate, which was 0.1 cubic meter per second. So I don't know why you're putting in it to minutes there when you have seconds, but you're welcome to. Oh, the K. Okay, so we had to convert the K at some point. So yeah, maybe it makes sense to just convert the flow rate to minutes. So as long as you get the right answer, You're doing the problem right. It's just a different route. Okay, any other questions, issues? All right. So problem 2, we have a chlorine problem. Say chlorine is used as a disinfectant, added in the form of sodium hypochlorite. That'll be NaOCl. This completely dissociates to Na plus and OCl minus, and then the OCl minus can have this equilibrium reaction with HOCl. So the form of chlorine is then determined according to the known equilibrium reaction with that info given. We have a disinfection reactor that's treating a flow of 2,500 liters per minute. And then we have a few questions. So A, if the pH of the treated water is 9.6, what is the ratio of HOCl to OCl minus? What would that ratio be? So for a ratio, we're given a pH, and we know something about the equilibrium reaction. We don't need anything to do with the flow rate at the moment. So we can kind of set the flow rate aside. Who cares? Doesn't really matter how we are adding the sodium hypochlorite either. We just are set at a pH. All we have to do is figure out what is HOCl divided by OCl minus. Need to do this in molar terms. Given that we know something about the pH, and we know something about this equilibrium constant, which of course is our products multiplied by each other, products of this reaction divided by the reactants in that reaction. Okay, so then for part A, really what we need to do is just simply put in a value for H plus and solve the algebra. Right, so we know pH is 9.6, and remember, this is as if we're saying P of the H plus concentration, which means the negative log of H plus is equal to 9.6. Or we could say H plus is equal to 10 to the minus 9.6 moles per liter. Okay, so we know our H plus concentration. And to get from this guy over to here, really all we have to do is divide both sides by H plus and then flip it upside down, essentially. Or, however you want to describe it. You can multiply both sides by HOCl, divide both sides by OCl minus, divide both sides by Ka. Regardless, you're going to get your equation HOCl divided by OCl minus should be equal to this H plus over Ka. So that would be 10 to the negative 9.6 divided by 10 to the negative 7.54. Just looking at that number, we can kind of tell that the top number is a smaller number than the bottom number. We're going to be left with something like 10 to the 2-ish, 2.04 maybe, and 10 to the minus 2 is 0.01. Right, so it's going to be somewhere near that. Okay, when we put that into a calculator, it comes out to be 0.0087. So that is our answer to the ratio between the two. That means, and of course we could flip that if we wanted to look at it differently, but it essentially means there's almost maybe just over 100 times more OCl minus than there is HOCl, or 100 times less OCl as HOCl than there is OCl minus, however you want to say it. We could also make use of the fact that there's we could call it like a total chlorine would be one plus the other. We don't need that part for this problem, but that's an additional equation that we could add to this if we were given some information about how much is there. So don't really need this at the moment, but just keep that in mind. We might need it in the very next problem. So part B, and any questions there before I move on? I'm good on that. So part B, we have operators decide that a concentration of 2.5 milligrams per liter of HOCl must be applied to the treatment process. So if that's the situation, what mass of NaOCl should they add per second if the pH is kept at or lower than 7.3? So we have a new pH. We now have a mass target for HOCl. And now we need to know something about the total chlorine that we have to add. And we add it in the form of NaOCl. So this is adding a lot of pieces here because we're going to have to do some molar conversion between the milligrams per liter to moles per liter. Do our equilibrium. We have the new pH. Go ahead and write that down. H plus now is at least 10 to the negative 7.3. And I say at least because if the pH dropped any further, we'd have more H plus. That means we'd have more HOCl. So to just put it at that threshold gives us the at least. Okay, so we can solve the problem at pH 7.3, and that'll be fine. You could check it if you wanted to and make it more acidic, and you would recognize, okay, maybe your mass. Let's see, how am I saying this? If you were to actually increase your pH, you're not adding, your answer would be not as big as the answer for 7.3. And so you'd actually, to get the minimum, to answer it as a minimum, you'd have to increase. But anyway, so we're going to solve it at 7.3. And we need the flow rate that was given a moment ago. So I think that was 2,500 liters per minute from the problem. And we need HOCl to be exactly 2.5 milligrams per liter. That means, but that's in milligrams per liter, and we need to convert that into moles per liter. So there we need to get our molecular weight. Molecular weight for HOCl should be 52.45. At some point, we'll also need the molecular weight for NaOCl, and that one is 74.45. So each grams per mole. Okay, so then if we take this 2.5 milligrams per liter as our target, we can multiply it by the number of moles per gram, or same thing as dividing by the molecular weight, and of course convert from the milligrams to the grams. And let's see, so that would become 4.77 times 10 to the minus fifth moles per liter. Okay. Do I need to elaborate on that to walk you through that, or are you good on that? Okay, so we're going to take the milligrams per liter, change that to grams per liter, divide it by the molecular weight. That'll convert us from grams to moles. Okay, so that's for the HOCl that we need. So that's kind of the target that we have to meet. Okay, so the other thing we can recognize is, again, the total chlorine will be what is supplied as our NaOCl. On a mole per liter basis, any mole of NaOCl that we add is going to give us the total amount of chlorine that we have. That's our only source of it. For every 1 mole of NaOCl, we get 1 mole of OCl. and then the OCl is in equilibrium with HOCl. So anytime we add one molecule of it, we can get one molecule otherwise of either form. So 1 mole gives us 1 mole of OCl. We also recognize that this will be our HOCl plus OCl minus. Right? There's no other sources of it. Once it splits apart into some fraction of each, that's what it'll be. Okay, so we can actually already say that NaOCl will be equal to this number that we solved for, 4.77 times 10 to the minus 5th moles per liter, plus OCl minus. So we're working towards finding our NaOCl, the amount that we have to add. We're going to account for the fact that we have to add it continuously with the flow rate, but we'll do that later. So we're just trying to figure out what concentration total do we need to meet the concentration that is our target. All right, so then the question becomes, can we put OCl minus and substitute, given our equilibrium equation, and substitute it for the other things that we know? Because we do know that the HOCl concentration, we do know the Ka, and we know the pH. So we should be able to solve for OCl minus in terms of the other knowns. Okay, so here's where we're going to take our equilibrium equation. Ka equals H plus times OCl minus. So I'm going to kind of segment this a little bit, divided by our HOCl. So we can just take this equation, rearrange it to solve for OCl minus, and plug that rearranged equation into here. So this is, again, things you've done in algebra, we're just doing it with the theme of chemistry. So we're just taking a system of two equations here, going to rearrange to make a substitution. So we'll take our OCl minus and say that's going to be equal to Ka times HOCl divided by H plus. So there are our three knowns. So this will be 4.77 times 10 to the minus 5th moles per liter plus Ka, let me rewrite that a little bit, times HOCl divided by H plus. And then we can solve for that because we know the Ka, we know the H plus, and we know the HOCl. So when we do that, we should get a value that is 7.51 times 10 to the minus 5th moles per liter. Okay, does that make sense? So that gives us the amount of chlorine we need to add on a molar basis. So now all we have to do is convert that back to a mass basis to say, at any given time, how much mass concentration do we need? So we'll take this value and multiply it essentially by the molecular weight. So 7.51 times 10 to the minus 5th. This is moles of NaOCl per liter. Multiply it by our 74.45 grams of NaOCl per mole NaOCl. And we should end up getting a value for the NaOCl concentration. Needs to be 0.0056 grams per liter. So that's per liter of water that we are going to treat. And so then we can take that and essentially multiply it by our flow rate to get what amount of mass per time that we have to add, because that's what the question asked. Now, it also asks per second, so we're going to need to convert that. So we'll take this concentration, 0.0056 grams per liter, multiply that by, let's use this, 2,500 liters per minute. And then we'll go ahead and multiply this by the fact that there is 1 minute for every 60 seconds. Okay, when we do all that, we will end up arriving at 0.23 grams per second, or you could also say 230 milligrams per second. So either way, we are reporting a mass per second. Should be fine. All right, does that make sense? Okay. Problem 3, we have a membrane system. So we are considering a membrane filtration unit. It's designed to treat water in rural areas lacking major infrastructure. So we're using gravity to drive the water through a 0.22 micron membrane, and it houses 22 square meters of membrane area. The system is operated in a cross-flow condition using constant flux to meet a demand of 500 liters per hour of water. Little side note, it's not really important for too much, but just as a little context, I realized I didn't add in class. We can actually operate membranes with a constant flux to make a certain amount of water per time. That means we have to increase pressure as if resistance changes, or we could operate with a constant pressure, and then the flux itself might drop over time. Doesn't really matter too much. Don't think it'll be relevant on your exam or any of this. That just reminded me that that's a thing. In labs, we usually have a smaller scale system and have a way to keep our pressure constant, and then we can watch how the flow rate drops. In practice, usually we're trying to keep the flow rate constant so that we can supply a certain amount of water for people. So usually there's a difference between lab and application in that we often conveniently study it one way, but in practice we have to meet some demand. So if you're ever studying this, that's a small detail. Like I said, not too relevant here. That's just part of the description. Okay, and ultimately you can kind of understand the systems either way. It's just a matter of what's your basis of comparison. Anyway, okay, we're treating 500 liters per hour of water. It's at 30 Celsius, and we're given some value of how much pressure 1 meter of water stacked up on top of something provides. That's 9.8 kilopascals. So, question is, what is the flux across the membrane? What is J? Given these parameters, and we're asked to answer it in meters per hour to 3 decimal places. So we know flux, this would be the flow across some area. We have a few versions of flux. So we kind of have to take a look and see what we need, right? We have a formula sheet as well. We could also define flux as the transmembrane pressure, TMP, over total resistance times dynamic viscosity. So we have a few things to consider. We have some information that might be relevant, but let's look at it simply first. We're given a membrane system with an area. So we already know the area is 22 square meters. So if we have a flux across it, that's our area. And we're given a flow rate. It's operating to meet a demand of 500 liters per hour of water. Okay, so we have enough information to find the flux without going into the pressure or resistance or any of that. And we weren't given any information about the resistance either. So I think that's coming later in the problem, But at the moment, this is pretty simple. We just need to provide an answer in meters per hour. So we didn't need to convert our flow rate to meters instead of liters. It's already in hours. So Q is 500 liters per hour. But we need to convert that so that we can answer in meters per hour. So this would be, we'd say there's 1 cubic meter per 1,000 liters. So our flow rate would be 0.5 cubic meters per hour. Okay. So then we can find our flux. Should be pretty simple, 500, or rather 0.5 divided by 22. This will become 0.023 meters per hour. All right. So then part B says if the recovery rate for the membrane is 95%, that would be the water recovery rate, how much water must be fed to the membrane unit to achieve the required permeate flow rate? Also answer in liters per hour. Okay, so we know that the Q that we just used, the water that it's producing, that would be our permeate. That's 500 liters per hour. Without even going back and looking at our equations, we can probably tell to ourselves that, well, if we're keeping 95% of it, then we have to feed it 5% extra, essentially, because 5% has to go to waste. The math, might work out so that we need a tiny bit more, so that 5% of that tiny bit more is, is accounted for. So then we could just say the way we approach this is our recovery rate is the ratio of what's coming through the membrane to what we're feeding it, and that's what we're setting to 0.95. And here we'll see when we rearrange to solve for QF. QF will be QP divided by 0.95. And if we take 500 divided by 0.95, we should end up with, so this is our 500 liters per hour. So this will be 526.3 liters per hour. Okay. So pretty simple, pretty straightforward. You'll find a lot of the membrane problems tend to be fairly straightforward once you understand what it is that they're asking for. So problem C says when the membrane is clean, the membrane resistance is 1.8 times 10 to the 13th per meter. And the question is, how many meters of water are required to pressurize the membrane to yield 500 liters per hour of water? So answer in liters to 2 decimal places. And I'm sorry, I haven't been keeping track. I think I've been doing the decimal places correct, but yeah. Okay. All right. So now we have a resistance. Now we have to be thinking about the pressure required. So really, we probably do need to come back to this equation. And we'd have to look up at 30 degrees Celsius our dynamic viscosity. And in our lookup table, this would be 0.798 times 10 to the minus third, don't forget that part, kilograms per meter second. Okay, we are also given that every 1 meter of water is 9.8 kilopascals, so that'll give us a way to convert from the pressure that we solve for to meters of water stacked on top of the system. Okay, so then essentially what we can do is solve for the transmembrane pressure. We know the flux, we already calculated that. So this is going to be taking our J, which was .0023, is that? 0.23. Meters per hour. Multiply that by the resistance and the dynamic viscosity. Resistance given, viscosity we looked up, and it turns out the transmembrane pressure should be 90.7 kilopascals. So just thinking about it, the fact that 98 would correspond to 10 meters, this is going to be something like 9 meters, right? So we can take that, multiply it by 1 meter per 9.8 kilopascals. She get 9.25 meters. Bless you. Okay, makes sense? All right, one more part to this problem. We have during operation, the membrane fouls continuously such that 5 times 10 to the 12th per meter resistance is added every 20 minutes. How many meters of water would be required to supply the 500 liters per hour after 1 hour of operation? So how many meters to 2 decimal places? Now, I will say that giving a rate like this, we might start thinking about, oh, the rate of resistance added, and do we need a rate constant and stuff like that? Well, if you're thinking that way, good for you, because you're kind of really getting the theme of the class. But in this case, let's just not treat it that way. It's going to be a zero order. It's just 5 times 3 because there's 60 minutes. You know, there's 3 20-minute blocks in the 1 hour. So 3 times 20 will give us 3 times 5. So we're just going to take this, say the resistance added times 3. There will be 1.5 times 10 to the 13th per meter of resistance added in that hour. So we're just going to leave it at that. Nothing too fancy. Just as a way to say, all right, we have more resistance after an hour. Okay, so then the question becomes, how many meters of water? So it's kind of the same problem as last time, but now we've changed the membrane resistance. We still need the same flux, so that's going to stay the same. The pressure is what's going to have to change now that the resistance changed. Okay, so let's just go ahead and solve this. We'll say the transmembrane pressure, again, would be equal to J times RT times mu. And this time, the RT nu is going to be whatever the resistance was before, 1.8 times 10 to the 13th, plus the new stuff. So plus 1.5 times 10 to the 13th. So that should give us, what, 3.3? Per meter. So that's just the new value we need to put in there, and everything else stays the same. So 0.023 meters per hour times 3.3 times 10 to the 13th per meter times our dynamic viscosity, which was 0.798. Now, one thing I didn't mention here, but if you notice, we've got hours and seconds here. So that's something that we would have had to account for in our calculations. I think I must have glossed over that. Okay, so once we account for that, the transmembrane pressure should come out to be 166 kilopascals. Which means we can then take that and divide it by the 9.8 meters per kilopascal to get our height. 16.96 meters of water. Okay. Any issues? Questions? The unit conversions? The yeah, yeah, because this is not the. It was 9.8 kilopascals per meter. So I wrote that wrong. Thank you. All right. Okay. So I guess I have this set up kind of reverse order in terms of the sections we covered. So now we're going to go to a granular filtration system. And here we have one that's being designed to use granular filtration to produce 0.65 cubic meters per second of treated water. Consulting company has been contracted to design and install the filters. Each of them are going to be 70 square meters. It's a 7 by 10 size. And they should be able to provide a loading rate of 9 meters per hour with a 72-hour cycle time. That'll include 20 minutes for backwashing, 15 minutes for rinsing. And we have the following questions. So A, what is the effective filtration rate for these filters? So REF, we have an equation for that. If you recall, this should be our volume filtered minus the volume used for rinsing and backwashing. All that divided by the area of a filter times the total cycle time. So we need to find a few volumes, do a few calculations here. The area of the filter, kind of obvious, that's the 70 square meters. And in this case, we're not given any backwashing rate. So the best thing we can do is simply assume if there's nothing given, no information at all anywhere about a backwashing rate, I guess it must be set to the same default as the loading rate. And maybe good to just note that we're making that assumption. Now, if you were to make that assumption, but you were given some information about the backwashing rate, then you're making a bad assumption, right? So hopefully you would just be given the information, but in this case, we were not. The total cycle time is 72 hours. It's going to be important because we need to know looks like we need to solve for the time for filtration. We know that the time for rinsing is 15 minutes. Time for the backwashing would be 20 minutes. Of course, we could count these as 0.25 hours, 0.33 repeating hours, and then get our final filtration time by subtracting accordingly. So our time for filtration should become 71.37 hours. Okay, then we can use all those pieces of information to get our volumes and then solve for our effective filtration. So real briefly, the volume filtered would be calculated as the loading rate times our area of the filter. Just like we would consider the volume we could produce from a membrane, it's the flux, the loading rate, times the area, times the amount of time we spent doing that. Put in those numbers. We're already in hours, that's convenient. This becomes 44,993 cubic meters. We'll do the same process for the volume used for the backwash, 210 meters, cubic meters, and the volume rinsed will be 157.5 cubic meters. With all that, we can calculate our effective loading rate at 8.8 meters per hour, and we can double check that, yes, it is true that is a little less than our normal loading rate, which is exactly what we want to see, because if it was any higher, then somehow we've gained speed by wasting some water and slowing things down. Wouldn't make any sense, right? The loading rate during operation must be faster than our effective because we are pausing it to have some downtime. Okay, so then problem moves on and says how many filters are needed to meet the 0.65 cubic meters per second flow required. So now we have per seconds. We're going to need to do something to account for that because we're dealing with hours. Shouldn't be a big deal. What we're going to do is we're going to take the effective loading rate that we just calculated, 8.8 meters per hour, take that to meters per second. I don't have the number here, but so we might as well, got enough time to pull out the calculator. So we would just simply take 8.8, divide that by 60 to get to minutes, divide by another 60 to get to seconds, or just do that. So this would be what, times 1 hour per 60 minutes times 1 minute per 60 seconds. So when we put it in that form, we get this number, 2.44 times 10 to the minus 3. So small number of meters every second. Okay, anyway, we can take that then and say that the flow provided by any one filter would be that our effective times the area of that one filter. So we can get a flow rate then. Might as well do that too. Take this, multiply it by the 70 square meters. So this would be just one filter. And we're going to compare the flow rate of one filter to the total flow rate we need. That's kind of the ultimate goal. And so when we did this, that was 0.171 cubic meters per second of flow rate. So the Q total is 0.65 cubic meters per second. And we can divide that by some number of filters times the Q for one filter and solve for our answer, right? So we can say the number of filters should be Q total divided by essentially this QF. I don't know if I So we'll put it that way. And that should give us a number, the 0.65 divided by 0.17. That's going to give us 3.775. But we're not going to install a partial filter. So we must say that has to be 4 filters as our answer. I wouldn't take a lot of credit off, but I will take credit off for giving me a decimal value there because it simply doesn't make sense. Okay, so then to highlight that, the next question asks how much additional flow in cubic meters per second can the plant handle before new filters must be added. So what I'm showing you here is that part of a filter that was extra, actually gives us some extra capacity, given our design so far. So the question is, well, how much flow does that difference between 4 and 3.775, how much does that give us? One way we could do it is just simply say, all right, that amount should be some extra area of a filter, and then we can multiply that by our effective loading rate to get a flow rate. So the extra area would be 4 minus 3.775 times the area of one filter, 70 square meters. And this, I guess we could write that as there are 0.225 extra filters, right? So we can say this is 0.225 extra filters times the 70 square meters. And then multiply that by our effective loading rate. That will give us, as long as that's in meters per second, that should give us a value of 0.0387 cubic meters per second of water that is simply extra. So we could increase the capacity, at least of this part of our system, by that amount before we have to add new filters. So maybe a treatment plant would do that on purpose and say, well, our design says for today's demand we need at least 4 filters, but we think the city's population might grow a little bit in the next 2 decades. Why don't we just put in 2 extra filters? That'll give us the capacity. Since we're building it all now, if we have the budget, let's do it. And that might be a good way to go. All right, so that's all I have for you prepared. Any other questions, requests? All right, so keep in mind, next week, of course, we have the exam Tuesday. We have a guest lecture Thursday. I've reserved the right to quiz you on that. That'll be advanced oxidation kind of stuff. Be nice to my grad student. He's a great guy. Well, so is the other grad student who will proctor the exam. Be nice to her as well. And I'll see you in a week and a half.